And good morning, everyone. Hua. Almost. Try it again. Good morning. Hua. A special welcome to Secretary Young. John, it's good having you here. General Griffin, good having you here. General Wallace will join us later on. To our Nobel laureate, really great having you all with us this week. To our soldiers who are with us and their wives, academia and industry, and all the other important folks who have joined us in this 25th or silver anniversary for the Army S&T. I'm reminded that I'm supposed to start my presentation with some type of trivia, and I do have one. And then someone said, you know, at the end, if you keep it short, there may be a couple questions. And I said, well, I'm going to jump in early. I'll ask my questions first because we have all this brain power out here, and I know there are answers all over the place. So I have two trivias for it, and the first one actually was given to me by a well-known physicist who will go nameless, but his initials are John Parmentello. John went out and gave me a chart, and the chart showed Blue Gene, which is one of our fast supercomputers. And he said, do you know how many watts power the average human brain consumes? So that's my question to you. How many watts does the average human brain consume? This is audience participation, so any guesses will be appreciated. 30. We have 30. I've got 30. Do I have 30? I got 30. Can I get 31? Got 31. I got 31 back in the corner. Can I get 60? Can I get 60 over here? I got 60 over there. I got 120 right here. Anybody else? Half? 10. Okay. I thought we were getting down towards 0 or a half. You know, that's down around the fighter pilot level. And I can identify a little bit with that. All right, how about way in the back row back there? 7? Okay, well, let me tell you while you're thinking about the answer, let me tell you what your brain can do. Human brain, calculations, 10 to the 16. That's a lot of calculation going on per second. Weighs about 4 pounds, give or take, depends how big your head is. Takes up about 0.06 cubic feet. And let's talk about Blue Gene. Blue Gene weighs, several 100,000 pounds. Takes up a building about this size. Consumes about 2 megawatts worth of power, if I remember correctly. And calculates at 10 to the 15, not 10 to the 16 operations second. So, Blue Gene compared to yours. You consume a whopping 15 watts of power. Now, the well-known physicist said, well, yeah, Blue Gene's a little large, but if you give me about 4 billion years worth of evolution, maybe we can shrink that hammer down a little bit and increase it. Now, I say that because virtually everything that we will talk about in this conference, what we'll talk about this morning, I'll breeze through a few charts here to show you some highlights that you'll see later on, either here or down on the floor. Everything that we know is a result of someone's 15 watts of power. The challenges that we will lay before you today will be met by someone and their portion of their 15 watts of power today, tomorrow, or somewhere in the future. That also applies to the students back there who are using their 15 watts of power right now. Okay, that's the first trivia. Let me have the next one. Next one is pretty easy. Next chart, please. Okay, who invented the battery and what inspired this great invention? And the answer is, next chart please, Volta. And it was a torpedo fish. I guess someone dissected the torpedo fish and realized that it generated its current by putting some layers together, dissimilar, that created the current and was separated. So Volta did the same thing with zinc, silver, and I think his blotter was actually leather, and put a little acid in there. And voila, you have Volta and the battery. Now keep that in mind because we'll come back to that a bit later. Next chart. We're going to go through some of the things that we're doing today, and we say it's the current force because a lot of this is showing up on the battlefield and has over the last 3.5 years, which is timely given the situation that we have right now. Logistics, we have precision airdrops. The Army has been doing that, so we can precisely put payloads down on the ground. The Air Force now likes that so much, they're actually buying it. Once we did all the development, they're now buying that from the production contract. I should charge them a little bit more money. Enhance lethality with acoustic gun direction devices. We also have networks. Some of you know a bit about our Blue Force tracking, which was actually in place as we started the war back in the 2003 time frame, and we've expanded upon that. Zinc air batteries, and once again back to Volta and what's going on, the quest has never ceased to try to figure out how you can get more power density in a smaller package, and particularly for soldiers, have less weight on their backside. And of course, survivability, very keen to what we're doing in Afghanistan and Iraq today, particularly with the RAM, which is our rocket artillery motor detection system, and then various survival equipments that we provided to soldiers. Next chart, please. Many of you in this room are very much involved with the future combat system. It's the Army Systems of Systems. First networked force, complete Army from the ground up. We've been at this in terms of this phase, the system development and demonstration phase, for over 40 months. And after 40 months, almost 43 months now, we are below cost. And last time I checked, about 6 hours behind on the schedule. That's not too bad. Given the size of this program, there are 18 major programs in this particular program. Then wrapped around a network, which connects everything, which in itself would be another major program, all focused on the soldier. It is, by outside experts, outside the Department of Defense and certainly outside the Army, the largest, most complex systems-to-system undertaking the Department of Defense has ever done. And so it speaks volumes for the team, government and contractor team, and academia, who allow us to be basically on schedule and on cost 3.5 to 4 years into the development. Now this is the well-known hurricane chart that the program manager shows from time to time. We thought by now, after a couple of years, it would have gone its way as everything else has to another way of depicting it, but it seems to say everything that needs to be said in one chart. On the outer ring, you'll see the spirals. Eventually, you'll see a spin-out one, which we will start delivering to an evaluation brigade next year in the 08 timeframe, FY08. That brigade is being stood up as we speak out at Fort Bliss and Wismar. And their task will be to take the first increment of technologies and work on that for about 2 years, from 08 to 10, and then put that into the field. And every 2-year cycle, we'll have more and more technology until about 2014, when we have all the technology put into a combat brigade, and that will be the first one into the field. A tremendous undertaking that connects equipment, soldiers, and the rest of our forces, that's the joint force, as well as coalition partners. Next chart. Some of the technology that we're looking within the FCS, if you could see the red triangles there, that would give you the time when we're at a technology readiness level of 6. But we have close-in protection, the active protection system that we have demonstrated several times now, and it does work. It's interesting to note just a few years ago, people thought it'd be next to impossible to get that system working as quickly as we have. The use of unmanned systems, robots, and you'll see some of those down on the exhibitors floor, both small robots that you can pick up and throw around to very large, several thousand pounds worth of vehicles that now are being worked and are working for us, the small ones in Afghanistan and Iraq, and the larger ones in test that allow us to track behind one another and get some of the load off the soldier. Network systems I've talked about earlier. Without the network, quite frankly, the FCS would not be the capability that we would want. To have the ability with all the sensors, whether that's a human sensor or inanimate sensors, tied to a network where you can see where the enemy is before he sees you and put a rock on their head before they put a rock on your head, is worth millions, if not billions. Lethality, the small one in the corner down here is what we call the rockets in the box. That's a cute little saying. You know, people think, well, that's nice little view graph, and you dump it off in the field, and there's a rocket there, and someone commands it, it goes up all by itself, unattended, life is good. Think about this. Who's commanding this? It's going to be a soldier, who in the past, when he had to call for fire, would get on the horn. If you could get the radio working, get someone at headquarters to talk to someone else, to get someone else, to get someone else, to eventually get some type of fire in on a target that now has disappeared. And heaven forbid if you had to wait on the Air Force. No pun intended, I used to be one of those Air Force guys. Now the soldier is going to be able to do that. Well, the soldier is going to do it. That smacks of a whole lot of different training for that soldier, ROEs for that soldier, different command and control for that soldier. So this is not just a materiel effort that we're in here with the Future Combat System. It goes across the entire Doppler PF. Everything that we do is changing as a result of the FCS. More importantly, it's already changing on the battlefield, particularly if you look at the strike brigades and the things that we've been asked to do as a result of the global war on terror. Next chart, please. Technologies for the warfighters. You'll see some of this on the floor once again. The soldier-machine interface, and not just putting a nice screen together and having someone sit down and take a look at that, but how do you get the involvement of specialists like yourselves, particularly in the soft sciences, involved with the decision-making that has to go on in the battlefield. And so you will find, particularly with the FCS, a number of folks from our laboratories, from industry, who are looking at how we think on the battlefield, how we make decisions on the battlefield, and how we can do that better. Doing that first, and then applying the technology. And then seeing how that works, particularly with the soldier-machine interface and how to make that better. Propulsion, both looking at, and power, looking at hybrid solutions, batteries, electrics, and fuel cells. And then unmanned sensors, to populate a battlefield so that we can see the enemy before they see us, or to put that airborne or even spaceborne. Next chart, please. One of my favorites. We have a UARC down with the University of Texas, industry, and us. And for several years, we've been working on the electromagnetic gun. Some of you are familiar with this. A few years ago, we challenged industry and academia and our Army lab, and basically my challenge was, let's see whether or not we can produce a working prototype by the end of this decade, 2010. We're doing this in conjunction with our partners from the Navy. We have some input from the UK, and our last review was just over a week ago. We believe that we'll be able to meet that date, if not beat that date, and have a capability that allows us, or a demonstration allows us to see the feasibility of actually making a capability for the Army and also for the Navy. We're also bringing in those who ultimately will use this. So TRADOC led now by General Wallace, who happened to be in that conference, in that meeting that day, along with General Griffin and a host of the staff. It's important for us to understand what this capability is, to help our scientists, when we get toward the end of this particular phase, figure out which way we're going to go next. I think this capability will revolutionize what we do on the battlefield, as much as gunpowder did when it entered the battlefield. Next chart, please. This just talks about how we could use that in the future and exploit the hypervelocity effects and increase viability. Next chart. Flexible displays. We have a center down at the with industry and with the university, Arizona State University, to see if we can build these displays, and we're making good progress there. That particular center has been open over 2 years now. And when we opened it, we were actually a year ahead because of all the work that had gone on the previous year in setting that up. Now, there are any number of reasons why we want flexible displays. Many are listed here. Glass is not ruggedized. It will break. It's not very flexible. It doesn't bend very well. If you shine light on it, it's very difficult to see through it, and a number of other things that we're trying to overcome with this new technology. Oh, by the way, since we're doing this at a university like Arizona State and the Sun Devils, we figure one of the first places we'll see it after we use it is on the quarterback's arm as he's looking at the plays for the next series of downs. Next chart, please. In the Bioinspired Areas, and here we're looking at gecko, but quite frankly, we're looking throughout nature to see if there are ways that we can, or things that we can learn from nature, and then try to mimic that somehow, whether we look at the IR capabilities of snakes or the ability for objects to replicate parts of their bodies, and a whole host of other areas. Now, let's face it, most of us flew here today. You got airfoils hanging out there, a piece of metal beating its way through the sky. Yeah, we copied a bird on that, and we haven't progressed too far from that in the last 100 plus years. Next chart. Other areas are in the signaling networks, and you'll see a really neat display downstairs, and an adaptive network, or how cells do sorting. And I mentioned earlier the uncooled IR that a number of species use. Next chart. Ultra-large systems. The folks in my office, and particularly Tom Kelly and others, will tell you that I've harped on this almost from the first day that I came here, and once we got on the quantum computing and a few things like that. The Future Combat System initially had 33 million lines of code to develop for its initial fielding. That will go up or come down depending on how we go through the next through this phase. So I asked a question one day: how can I do the 33 million lines of code using 10% of the people, 10% of the time, and 10% of the money? And just like this, there was a little pause there. So okay, let's flip the question. Give me 1 billion lines of code, new code, 100% error-free, all working, use the same number of people, the same amount of time, same amount of money that we're currently using for the Future Combat System. And once again, there was silence. And I said, we have a barrier in front of us. And regardless of how well we tweak the tools that we have today and improve those, we will never overcome that barrier. To me, it's like going through the sound barrier with a biplane. You can polish the biplane, you can put bigger engines on that biplane, you are not going to crack the sound barrier. So I look at this as a basic research project to begin to go back to the basics. So we asked the folks at Carnegie Mellon, who then got a team from across the United States. They worked for a year and came back to us and said, we believe it can be done. It will take time. And it's going to have to be multiple disciplines. And then they prioritize some areas. So now we're socializing that with academia, with my colleagues in the Defense Department, and with industry. One, to see, am I full of smoke? We're doing fine the way we are. or the holes in the argument, shore those up, and then press on. Because I've got to believe that 100 years, 50 years, maybe 20 years from now, we will have systems that we will want in the Department of Defense, in academia, in the commercial world, that are going to have far more than a few 100 million lines of code with them. And there's no way we can get there from here without a new approach. The other thing I said as they were going out the door, I'm not sure why we're using Boolean algebra, zeros and ones. You know, I understand why we started that way. I'm not sure why we still do it today, because we can bias devices on, off, and several places in between. And the last time I checked, Mother Nature doesn't use 2. She uses at least 4. So there must be a better way. Next chart, please. Nanotechnology, and once again, industry and our colleagues up at MIT working in this area to look at things like a virtual human, a holodeck, bandwidth, and a whole host of others. Next chart. Finally, who gets to do this? This is a hint. Goes back to those 15 watts again. You know, everything that we do in the Army, and I'm sure this is true for any military or for our foreign partners who are here today, it starts with people, and people are central to everything that we do. Absolutely central. Institutions, you know, do not transform. They don't make this thing happen. People do. Organizations and platforms do not transform. People do that. Units don't train. They don't stand ready. They don't grow and develop leaders or scientists or engineers. They don't take risks. They don't sacrifice on behalf of the nation. People do that. And people just like you. And people just like the young people back there who are coming in behind us. Everything that we have in the Army really starts with a piece of technology, whether it's coming off the shelf, coming out of our labs, coming out of academia, coming out of industry. Some bit of technology took place there. And behind that technology is some person who has spent a lot of time thinking about that technology and perfecting that technology, or engineering that technology, or producing that technology, or fielding that technology, using that technology, and maintaining that technology. People do that. And without you, we are absolutely nowhere. A reporter asked me this morning, what's the biggest challenge in the Army when it comes to S&T and so forth and so on? And I'm sure the reporter wanted to hear, well, there's the budget and we need more money and so forth. And my answer is people. It's people. We are not pumping out enough scientists and engineers in this country. That's a problem beyond the Army. That's why we're into e-cyber and other activities to draw youngsters into this business. Brain power is what makes our Army strong. Brain power is what makes this country strong. And brain power will keep us going in the future. So God bless you. God bless the great work that you're doing. God bless our soldiers, our military. God bless America. Thank you, ladies and gentlemen. Have a great conference. Hua.